Okay, so 4.6 is the last section in chapter 4, and it's the meatiest. Okay, so we're talking about rational functions. And rational functions is lumped together in the same chapter unit as polynomials because of what a polynomial function is, right? So we've been focused in the other sections in looking at polynomials and figuring out how to identify different characteristics of polynomials, right? We're still going to use similar approaches for finding characteristics of rational functions, which are ratios of two polynomials. So whenever the numerator is a polynomial function and the denominator is a polynomial function. The difference between polynomials and rational functions, polynomials are just known to be smooth continuous curves whose implicit domains are all real numbers. Because rational functions have that denominator, you have to think about excluding values that would make the function undefined, meaning that would make the denominator equal to 0. The values that do end up making the denominator equal to 0 correspond to discontinuities, which we've already talked about. So they correspond to either removable discontinuities or non-removable discontinuities. And remember, removable discontinuities manifest graphically as wholes, or like when the function is actually defined as something else. This happens with piecewise functions. That's not going to happen with rational functions. So in thinking about rational functions, our discontinuities will either correspond to wholes or they will correspond to vertical asymptotes. Rational functions do not have jumps. Okay, so the removable discontinuities will manifest as wholes. Non-removable discontinuities will manifest as vertical asymptotes. Okay, and we're going to look at how to determine, like given a function, how to determine what type of discontinuity the domain restriction corresponds to. Are we getting warm? Should I close the door and put the air on?
Yes, please.
Yeah? Okay. That's not the right one. Knox, can you grab the remote for me over there? Do you see it on the side? It's around the corner.
Oh, yeah.
Thank you, Sophia. Oh, up.
Oh.
Do you see it? Perfect. There we go. Okay, it'll cool down quickly. Okay, so first of all, if we have a given rational function, let's think about identifying the domain of the rational function, which is same approach as what we've looked at before. For rational functions, our domain restrictions are always going to come from excluding values that would make the denominator equal to 0. In order to identify where the denominator would be equal to 0, it's helpful for us to get the denominator, well, the numerator and denominator into factored form. For this particular rational function, x minus 2 is already linear. It's not going to factor. But we can think about factoring the denominator. So we can rewrite r of x as x minus 2 over, what is that? X minus 4x plus 1.
Why is your thing so laggy?
Is it?
Yeah, when that happens, you have to close Notability. If you just like close Notability and reopen it, it will like.
It might be because I'm screen recording.
Oh, that could be it too. Like sometimes when I'm using like my Notability at home to do my work, it like starts lagging.
Okay,
Like,
let's see. Sometimes this happens.
that seems better.
All right, we'll see. Okay. But then when we look at this, we can immediately see what can x not be equal to. Is it still lagging? No, not for now. Okay, let me know if it does it again, okay? 4 or negative 1. Okay, so if we were thinking about stating the domain in interval notation, we would say, okay, negative infinity to negative 1, and then we want to exclude negative 1 using parentheses up to 4 union 4 to infinity. Okay. Both of these discontinuities correspond, or both of these domain restrictions end up corresponding to non-removable discontinuities because graphically they represent vertical asymptotes. And the way that we know that is because if we were to plug in 4 or -1, do you see how we would get a non-zero real number in the numerator? Like if we plug in 4, we'd get 2, but we would get 0 in the denominator. That is an indicator that there's going to be a vertical asymptote. So we can classify and say there's a non-removable discontinuity, or actually there's 2 of them, right? At x equals to -1 and x equals to 4. And that's because both of these discontinuities correspond to vertical asymptotes.
We just write VA.
Sure. If you think back to like the simplest rational function that we had talked about a couple days ago, 1 over x, remember how 0 corresponds to a vertical asymptote? If you plug in 0, you'd have 1 over 0. So we know that each of these values corresponds to a vertical asymptote because after direct substitution, you get a non-zero real number over 0. Are we okay with this? Sort of review. Like you guys could have told me those were vertical asymptotes, yeah?
Yeah.
Yeah. What's new is like we're linking it up with the fact that we call those non-removable discontinuities, right? Okay, let's look at another one. So same idea. So we have this rational function. In order to determine domain, it's helpful for us to get the numerator and denominator into factored form because then that allows us to see, well, what values do we have to exclude from the domain? Can't factor the numerator, but the denominator can factor to, what is that? X plus 3x minus 1. Remember how when we were creating functions, new functions from other functions, I said state domain restrictions. Take into account domain restrictions before you simplify the equation. Still true here. So even though we will be able to cancel the common factor of x minus 1 in the numerator and denominator, we still want to make sure that we are going to take into account the fact that x can't be equal to -3 and x can't be equal to +1. So the rule for g of x can be rewritten as 1 over x plus 3. And that's actually a graph you guys know what it looks like, right? Like that's 1 over x shifted to the left 3. However, there are 2 domain restrictions. If we go ahead and graph this, so y equals x minus 1 over, here I'll put it in the factor form, x minus 1 times x plus 3. So you can see the graph looks like 1 over x shifted to the left 3, right? Like it looks like the simplified version of this equation. If I even type that in, y equals 1 over x plus 3, they look like they match up perfectly. Except for at x equals to 1. Where if I get close to 1, there it is. Do you see what it says there? That 1 is undefined. So if we're just thinking about this, especially the way that they're showing it once my finger's on there, that means as the function is approaching, so as x is approaching 1 from the left and the right, the function seems like it's approaching a similar value, right? Like it looks like the graph could be continuous if you were to just fill in that single point. Meaning at x equals to 1, would that be removable or non-removable discontinuity? Removable, because we could think about removing the discontinuity if we could just fill in the point at x equals to 1. This is what we call a hole, or referred to as being a hole in the graph. So taking a step back, let's go ahead and state our domain for G. Negative infinity to -3, union -3 to 1, union 1 to infinity. We've seen the graph looks like 1 over x plus 3, right? 1 over x shifted left 3. At -3, what's happening graphically? What's happening graphically at x equals to -3? Yeah, a vertical asymptote, right? Which we would classify as a non-removable discontinuity. So there's a difference here. So we say there's a non-removable, this one's pretty straightforward. There's a non-removable discontinuity at x equals to -3. Part of that is because, well, the reason that is true is there's a vertical asymptote there. And again, if we use direct substitution in either of these, don't we get a non-zero real number over 0? Versus at x equals to 1, if we substitute 1 in up here, what happens? If I plug 1 into the numerator, what do I get?
0.
If I plug 1 into the denominator, what do I get?
Oh, it's fine. Oh, undefined.
0. You would run into what we call an indeterminate form. And I'm just planting the seed for now, but this is an indeterminate form. It's meaningless, but it does, besides the fact that it indicates that the function's undefined. So when that happens, right? So this is different than whenever we plug in -3 and we get a non-zero real number over 0. When you plug in a number and you get 0 over 0, it's because there's a common factor that's causing the 0 over 0 in the numerator and denominator. They can cancel, but it still causes a domain restriction. That's why the graph looks like 1 over x plus 3, but it has that extra domain restriction. So x equals to 1 corresponds to, as we saw, a removable discontinuity, which graphically we refer to that as being a hole. And that's because you run into 0 over 0, right? The indeterminate form with direct substitution. Now, if I go back over to Desmos, if I could fill in that point, I'm going to zoom in a little bit here. So as I'm getting closer and closer and closer to 1 from the left, what does it look like the y values are approaching?
0.25.
0.25, doesn't it? And then if I go from the right side, if I go down towards 1, doesn't it also look like it's approaching 0.25? Do we see that if we were to plug in 1 here in the simplified version of the equation, wouldn't we get 1/4, which is 0.25? So 1 comma 1/4 is the ordered pair that represents the whole. Remember, a removable discontinuity is the function seems like it's approaching a number from the left and the right as x is approaching that value where the discontinuity is. Like you would want to just be able to fill in a hole, like by filling in like that single point. So we're saying that the point that we would want to replace the hole with is 1 comma 1/4. And that's because we know there's the domain restriction at 1. We know the graph looks like the simplified version of the equation. So if the graph looks like this, then if we plug 1 into the simplified version of the equation, it's going to give us the y value that we would want to fill the hole in with. Are we doing okay with this? Did we do holes this last year? No. Okay, so this is new. Okay. So holes, this is a lot of words. You can read it again later if you want. Holes are a type of removable discontinuity. You guys, I have taught generations of pre-calc and calculus students to spell removable wrong. There's not supposed to be an E here. And I've edited most of my documents, but there's still some that show up. So holes are a type of removable discontinuity because the function seems to be approaching the same value from the left and the right, but the point is not actually defined. Holes can occur when there is a common factor in the numerator and denominator that can be divided out. The graph of the function will look like the simplified version of the equation of the function, but will have the domain restrictions of the original equation. Because of this, you could think about how you would want to remove the hole by evaluating the simplified version of the function at the x value of the hole. This will give you an ordered pair that would make the function continuous at that point if you were to plot it, like if you were to remove it. Again, you cannot actually remove a hole from a graph. And a common factor is not a given for a hole or removable discontinuity. A non-removable discontinuity would actually trump the removable discontinuity. And I'll give you an example. So if we had something like y equals to x minus 1 over x minus 1 squared, where just looking at the rule here, you're like, x can't be equal to 1 is the only domain restriction, right? And we have a common factor. So a lot of students want to be like, oh, there's a common factor that cancels. That must mean it's a hole. But if you look at the simplified version of the equation, remember the graph looks like this guy. What's actually happening at 1?
Undefined.
Well, it's undefined, but graphically what's happening at x equals to 1? It's a vertical asymptote, right? Like this is 1 over x shifted to the right 1. If we were to plug in, well, here we get 0 over 0. In the simplified version of the equation, if we plug in 1, we get 1 over 0, which corresponds to a vertical asymptote, which means that x equals to 1 is actually a non-removable discontinuity. Right? because that is a vertical asymptote. So you want to be careful, and we're going to go through this more in classifying your discontinuities, though. Just because it's a common factor doesn't mean it's necessarily a removable discontinuity. Is everyone still with me to here? We're going to talk even more about non-removable discontinuities, and then we're going to start talking about end behavior. Okay. Are we locked in? Are we ready? Asymptotes. I hate the way that algebra and pre-calc textbooks present asymptotes. I think it really confuses students in how they present it, because students start thinking of all asymptotes as being discontinuities, or like not being allowed to cross asymptotes, which isn't the case. There are different types of asymptotes. What an asymptote actually is it's like an imaginary line that guides the behavior of the graph. We can I've told you guys before, I kind of like to use like, my brain, I feel like, really loves flow charts, or like kind of like the tree charts, you know? So asymptotes are just lines that guide the behavior of a function, right? A function approaches these different imaginary lines, not imaginary like imaginary numbers, but just like they're not actually part of the graph. And we use these lines, these asymptotes, to communicate about the behavior of the graph and have better understanding of what's going on with the graph. So there's two types of asymptotes. There are vertical asymptotes, which we just talked about, right? They're non-removable discontinuities, okay? The line x equal to a is a vertical asymptote for the graph of a function if f of x either increases or decreases without bound as x approaches a from the left or the right. We talked about this the other day when we were talking about non-removable discontinuities. When a vertical asymptote exists, it means as x approaches the number where the vertical asymptote occurs, the function is either going to positive infinity or negative infinity. You can think about 1 over x, right? If f of x is a simplified rational function, so if the rule, like all common factors have been canceled, where the numerator and denominator have no common factors, then the graph of f of x has a vertical asymptote wherever the denominator is still equal to 0. Because if you were to plug in wherever that value is, you'd get a non-zero real number over 0. When we are talking about the behavior of the function as it approaches a vertical asymptote, we're using that notation that we were using for talking about end behavior of a polynomial. So like we can think about like as x approaches a, and I kind of showed this the other day, but we don't like to write out as x approaches a from the left. We use a notation, like a shorthand, and we put a minus where the exponent would be. So this means approaching from the left. My iPad's getting really, really hot. Let me know if it starts lagging again, because I think it's working really hard as it's recording. So it means approaching, as x approaches a from the left, then f of x, if there's a vertical asymptote, then f of x is either approaching positive or negative infinity. And then the notation for x approaching a from the right, you could probably figure it out, is a plus and f of x is approaching positive or negative infinity, and you would have to determine which one. So we've talked about identifying vertical asymptotes. Vertical asymptotes are non-removable discontinuities. They correspond to domain restrictions. A graph cannot cross a vertical asymptote. Like, it does not intersect a vertical asymptote. Whereas the other types of asymptotes, a function could intersect or cross. So the other type of asymptotes that we talk about, and I think you've talked about one of these and not the other, is end behavior asymptotes. So end behavior asymptotes mean, like, a function has an end behavior asymptote if as x is getting infinitely large or infinitely small, the graph starts behaving like a line. Either a horizontal line, which I think that's what you guys have talked about previously, or like a positive or a negative sloping line. Now, rational functions can also have other types of end behavior. We'll talk about that. That's not like an asymptote, like not linear. But our focus in identifying end behavior for rational functions is mostly going to be when end behavior is linear. So when there's either a horizontal asymptote or what we call a slant asymptote. For end behavior, we're always thinking as x approaches positive or negative infinity. So in the case that as x approaches positive or negative infinity, the function is approaching a number, then we say that there is a horizontal asymptote at y equals to that number that describes the end behavior of the function. Like, if you were to zoom out on the graph starts to look like it's trending or like merging with that horizontal line. If the end behavior model of a rational function is linear, like y equals to mx plus b, or y equals mx, that means that the function will have end behavior similar to the line that has the same slope as the end behavior model. We're going to talk about identifying an end behavior model here in a second for a rational function. The equation of the slant asymptote gives an even more accurate description of how the function is approaching positive or negative infinity as x approaches positive or negative infinity. And just to kind of clarify, so end behavior model is like what we've previously talked about. Right, the EBM. And when I say model, I'm talking about like a reference, like it's something that's a reference. So it's this simpler function that you can identify, that you know the function that's more complicated that you care about has similar end behavior too. So EBM, if it ends up being in the form y equals mx, then that means that there's a slant asymptote that would be in the form of y equals mx plus something. And you have extra work to do to come up with that plus something. Okay. And then this is kind of an important note that students like always kind of mix up. End behavior is not a type of discontinuity. A function can cross an end behavior asymptote infinitely many times. It's just not at the ends, like not as x is getting closer. Well, actually, there's even some not rational functions necessarily, but other types of functions that have end behavior asymptotes that just keep crossing infinitely many times. Vertical asymptotes are a type of discontinuity. End behavior asymptotes are not. Okay, so we're going to do a little bit more practice with identifying vertical asymptotes, and then we're going to get into our end behavior asymptotes and put it all together to sketch graphs of rational functions. Are we doing okay, you guys? It's Friday afternoon. You have under an hour and a half. And I'll give you a little break around 1. We can do it. We're so close. Don't do that. Okay, so for finding vertical asymptotes, we have our rational function. We're like, hey, let's factor the denominator so we can see domain restrictions. Okay, so what does that factor to?
Minus
2x plus 5, x minus 6.
Yeah, plus 5 minus 3?
I think minus 6, I thought.
6
Isn't
and
it 2
5.
times 15?
Yeah, it's 6 and 5.
Yeah, 6 and 5.
Negative.
Nah.
Negative 6 and 5.
Yeah. I think it's 5 minus. It wouldn't.
What are you talking about? Wait, am I
Am
I out of it?
Isn't it 5
minus 6 plus minus 6x plus 5x would give me negative x.
Yeah.
5 times negative 3 is negative 15.
But don't you do 2 times negative 15? Am I dumb?
Isn't it?
It's like the AC.
You're not dumb, but I think you're maybe a little out of it right now.
Isn't that-
Like,
No,
I
isn't
don't.
the AC thing? Isn't it like 2 times 15?
I know, but
That's to solve it.
Yeah.
Oh, okay.
You guys are making me question.
Wait,
That's
I'm
no,
confused.
it's like
What would you be solving right now, you guys?
It's like a method. You like multiply the first and last thing, and then it's like what, negative 30, and then you figure out what like adds to the middle.
And then it would be 2x squared, and then whatever adds to negative 30.
Are you talking about like to factor by grouping?
Yeah.
Okay.
I think you thought it was like x squared.
I did guess and check. I don't really follow. I think I factored this correctly.
Yeah, that's right.
Yeah. Okay.
Food a cookie.
Okay. So looking at that, we can say x can't be equal to, there's no common factor to cancel, which means no holes, no removable discontinuities. So both of these domain restrictions correspond to what graphically? Vertical asymptotes. So we can say there's a vertical asymptote at each of those x values. So at x equals to negative 5 halves and x equals to 3.
Because at is, when you plug it in, it's like over 0.
Yeah, because if you were to plug in either of those values, you'd get a non-zero real number over 0. So that means vertical asymptote. Okay, let's look at the next one. We have some factoring to do in the numerator and the denominator.
There's gonna be a hole.
Is there? Okay, so if we factor out an x in the numerator, factor the denominator. So factoring this, I would be thinking about factors of 12.
Well, we do that when it doesn't have anything in front of it.
Okay. So minus 4, minus 3.
Yeah.
Okay. So remember, you want to think about domain restrictions before you cancel anything, before you do a major simplification that removes a domain restriction. So x can't be equal to 4 or positive 3. But x minus 4 can actually cancel to help us with figuring out what's going on with the graph. So x over x minus 3 is the simplified version of k of x. So thinking about what's going on at each of those domain restrictions, well, what's going on at 4?
A whole.
It's a hole. And how do you know it's a hole?
Because if once you, I don't know if I'm explaining well, but like you can simplify it out, so it's still, there's still a restriction there, but because it's like you get rid of it.
Yeah, so if we were to use direct substitution into the simplified version, what happens?
Real number.
What do we get?
Into the simplified one?
Yeah, if you plug it into the simplified version, what do you get? What is it?
4.
4. We get 4. That means that we would want there to be a point at 4, 4, but we know better, and we know that the function is actually undefined at 4. So we would want there to be a point, or we can say that there is a hole at 4, comma 4. And again, that 4, this comes from plugging in here. What's going on at 3?
Vertical asymptote.
Because
Because it's on the denominator, we can't have 0 in the denominator.
yeah, if you plug 3 into the simplified version of the equation, right, which is what the graph looks like. If we don't know what it looks like yet, but like we're getting there. If you plug 3 into the simplified version of the equation, we get 3 over 0, which it means it's still undefined, and that corresponds to a vertical asymptote. So we can say a vertical asymptote at x equals to 3. Now, for graphing, we are going to want to figure out, well, what's the function approaching as x approaches 3 from the left and the right? So in order to do that, right, like because we want to think about as x approaches 3 from the left, what's k of x going to be approaching? It's going to be positive or negative infinity, but we want to know which one. So the way that we can do this is we can pick a value that's close to 3 on the left, and we can think about plugging in to the simplified version of our equation. So like to me, a value that would be really close would be like 2.999. So if I thought about plugging in 2.999, even 2.99, right? 2.999, the numerator would be positive, the denominator would be negative. A positive divided by a negative is a negative. So that means that k of x as x approaches 3 from the left, because we're choosing a value that is super close to 3, just not at 3 on the left side. If we plug in that value into the function, it gives us a negative value, which indicates that k of x would be approaching negative infinity. Next.
If it said approaching on the right, would you pick a value to it?
Yes, let's do it. So as x, we could say as x approaches 3 from the right, we want to know, is k of x approaching positive or negative infinity? We got to think about it. So like a value to the right could be like
3.001.
yeah, or like 3.01, something like that. So 3, and you could, this is essentially side work. You don't have to write it out. It's what k of x is approaching that you should be able to answer. But notice how that would be a positive over a positive, which means when you plug in that value that's really close to 3 on the right-hand side, it means that the function is approaching positive infinity. Okay, it went a little overkill on that one. All right, we are going to talk end behavior and end behavior asymptotes and identifying those. And then we will do a little break and then we'll get into the actually graphing rational functions. Is that out of excitement? Is that excitement, Knox?
Yeah. Very, very exciting.
All right, are we ready to lock in? Alex, you might want to go in sport mode here. All right.
Oh, this is.
Other reasons
I didn't
for
realize you
these,
had Crocs on. Because who wears Crocs?
Me.
My kids wear Crocs
Oh,
all the time. But I make my kids go in sport mode all the time because I'm worried they're going to eat it when they're wearing their Crocs and running
I wore
around.
Crocs to school for one day and I never heard the end of it.
Did you laugh at a kid?
I didn't laugh at him.
scooter?
I was driving by.
You hit him?
Okay.
A kid on like little 3 wheels.
Do we need a quick stretch break? Like not leaving the room, but do we need to like stand up and stretch for a sec?
We're ready.
Let's do a quick stretch break. Everyone stand up. Stretch. Stretch. Maybe do some, twist, don't hit anybody.
We gotta do the miss.
Okay, we're ready.
You miss ups like weird.
We gotta do the miss press video.
No, the shoulder one? That was
What it was?
What do you mean? I liked it. It was a little workout.
It was like
I remember
Qigong.
my science teacher in like 8th grade told us before test assessments to do this in front of our eyes and that it was supposed to do something, and I'll never forget it.
Am I gonna ace on my test now?
I don't know. I don't know. All right, ready? Down. Okay.
Don't study for the SAT, that's what you need.
Okie dokie. Now, oftentimes for determining end behavior and like asymptotes for rational functions, you'll see that the textbook usually gives you like this chart and they're like, if the degree of the numerator is less than the degree of the denominator, there's a horizontal asymptote here. If the degree of the numerator is the same as the degree of the denominator, there's an asymptote here. If the degree, right? So they present it like that. And you can memorize it and you can identify asymptotes correctly. But I don't think that does a very good job of helping you understand why asymptotes, what they really are and why they occur. So I like to reference a function's end behavior model, which we talked about with polynomials. Remember what the end behavior model was for a polynomial function? What was it?
Largest coefficient.
Not largest coefficient, exponent. The term with the largest exponent. Okay, well, rational functions are ratios of two polynomials. Oh, I have a typo here, you guys. Can we fix it? These should not, because the exponents do not have to be the same. Let's make this into M. Here, I'm going to write it in red so you can tell that's where I edited.
Wait,
M.
Just add an M to it.
M. There you go. There you go. Okay. So this is our function that's a ratio of two polynomials. As x gets infinitely large or infinitely small, again, we can think about the terms as being at a tug of war with each other. In the numerator, who's winning the tug of war as x gets infinitely large or infinitely small?
First one.
Yeah, the term with the largest exponent. In the denominator, who's winning the tug of war?
Both the biggest, the box best.
This one. So it's this ratio.
Take this ratio.
It's this ratio of the terms with the largest exponents that ends up being the end behavior model. EBM for a rational function. So y equals a sub n times x to the nth power over b sub m times x to the m power.
Ooh.
So those two leading terms, that ratio is the end behavior model, meaning, and that's a simpler function than the rational function that you're trying to figure out end behavior for. So it means that your rational function that you're concerned with has the same or very similar end behavior to this function. This is what the textbook presents. And we're going to talk about why and look at examples. But we're going to be thinking about the end behavior model. So the textbook is like, okay, when the degree of the numerator is less than the degree of the denominator, then there's a horizontal asymptote at y equals to 0. When the degree of the numerator equals the degree of the denominator, there's a horizontal asymptote at y equals the ratio of the leading coefficients. And then whenever the degree of the numerator is greater than the degree of the denominator, there's no horizontal asymptote.
We did this last.
Yeah. We're gonna try and like go a little bit deeper here though, okay? And reference end behavior so you hopefully can understand it even a little bit better. But it's great. If you're at the point right now where you're like, I recognize this and I know how to identify when there's horizontal asymptotes, that's wonderful. That's a great place to be to build off of. So we're hopefully going to help you with your understanding of like how these manifest. Okay, so let's think about an example of a rational function where the degree of the numerator is less than the degree of the denominator. So how about like y equals to x over x squared plus 2? So in this case, the EBM, the end behavior model for this function would be this ratio, y equals x over x squared. Did Ms. Bertrand talk about end behavior model?
Nope.
No, okay, that's okay.
It's just HA.
That's good. No, this is good. Now we're talking about it. Okay, so y equals x over x squared. What does that simplify to, you guys? 1 over x. And you guys know what 1 over x looks like, but we can also do the numerical analysis where if we think about as x approaches positive or negative infinity, what is y approaching for 1 over x? If you were plugging in large numbers, 1 over 1,000, 1 over 10,000, 1 over a million.
Negative.
No, hold on. So 1 over 1,000, 1 over 10,000, 1 over 100,000, 1 over a million, 1 over a billion.
0.
Those values are getting smaller and smaller and smaller, right? Like we'd have 0.01, 0.001, 0.0000001, right? So we're trending towards 0. Will this ever be 0? No. But the values are getting closer as x gets infinitely large or infinitely small. Those values are trending towards 0. When as x is approaching positive or negative infinity, the y values are trending towards a number. That's when we say, hey, end behavior can be described by the horizontal line y equals to that number. So in this case, it would be the horizontal line y equals to 0. Do we kind of follow that? Sort of, kind of. Okay. Let's look at an example of a rational function where the degree of the numerator is the same as the degree of the denominator. So how about like 2x cubed minus 5x plus 1 over 3x cubed plus x squared minus 7. I know, I'm just making it up. end behavior model here is that ratio. What does our end behavior model simplify to?
2x over 3.
Careful.
Is that cute?
That's a 3.
Oh, I thought that was a 2 on the bottom.
It was just my poor handwriting. So, sorry, what does that simplify to?
2 over 3.
2 over 3, which, oh my gosh, y equals to 2 over 3. Isn't that just a horizontal line? So what that means is that this function, this rational function, has the same end behavior as the horizontal line y equals to 2/3. So we can say, as x approaches positive or negative infinity, well, yeah, y is going to approach 2/3. The same way that the horizontal line does. Why are we laughing?
Yeah, yeah.
Are we laughing because we're feeling really great about this, a little overwhelmed, or it's funny and I'm missing something?
No.
A little overwhelmed,
Yeah.
but I think we'll get through it.
I think so too.
We got
I also
through
think you
dialectics.
have the entire weekend to like let this marinate, you know?
Can we leave the problem on the board?
You're gonna get to problems
Chill.
on the board.
Oh.
We'll get there. Don't you worry.
Oh, that's how many else I'm trying to be.
All right. And then let's look at an example of a rational function that has the degree of the numerator is larger than the degree of the denominator. How about like 3x to the 4th minus 5x plus 1 over x squared minus 4.
Ooh, this is gonna be good.
There is no.
Well, our EBM would be y equals 3x to the 4th over x squared. What's that simplify to? 3x squared. So that means, you guys, the end behavior is going to be like a quadratic. Like y equals to 3x squared. Meaning, as x approaches positive or negative infinity, the y values are going to approach positive infinity. Similar to y equals to 3x squared. Okay, I would like I'm going to give us a quick break. I get it. This is a lot. So I'm going to